All right, moving on with our chapter review is lesson 1-4. I'm going to define some things first. So we have our recursive definition. And remember, our recursive and our explicit definition are the same thing, just written in different forms. Okay, so our recursive definition is an equals, and we have our set notation, a1, where n equals 1, and a to the n minus 1 plus d, where n is greater than 1. Remember, those intervals are always going to be the same. All right, and then our explicit definition is the same concept as the recursive, but it's written in a little better form that we're used to, and it's the one that we're going to use the most often. So we have an equals a1 plus d times n minus 1. I'm going to make a little key over here. And a key is just with labeling things of what they're supposed to be. So looking at A1, what does A1 stand for? What does it mean? Remember? A1 in a sequence is our first term. A1 is the first term. What does n stand for?
Number of terms.
Number of terms. Yep. N is the number of terms. What does D stand for? Difference. Difference. What also helps us remember, that's the pattern that's happening. Okay, and then AN, what does AN stand for? In one of our equations, we consider it the last term, but it can stand for any term, depends on which term you're talking about. Okay, and as an example, if I talk about a to the 6th, that means that's the answer to the 6th term. Okay, so these two right here kind of go hand in hand. So AN in an equation can stand for the last term, but it can also stand for any other term in the sequence depending on which one you're talking about.
Does it have to be A6 or can it be?
Specifically, I want to look at an example. If I'm asking for what is the 100th term of the sequence. Okay, underline, put a star. We're going to use this equation to help us answer that question. Okay, the recursive and the explicit, you might be asked questions to write those specific answers. Okay, but I also want to say what is the 100th term. So I need to back up. It is going to be A100. I got ahead of myself. We're going to look at example number 24 in your book to answer this question.
We're not doing that one?
We are, but it's with example 24. We got to do some things first. So that one is, the sequence is 5, 9, 13, 17, and 21. Okay. First, we need to figure out what A1 is. What's A1?
Oh,
5. A1's the first term, so A1 is 5. In this equation, I also need to know what the difference is. How do I figure out what the difference is?
I just subtracted 4.
How do I get from 5 to 9?
4
Plus 4. 9, 13?
plus 4.
Yep, double check all of them. 13 to 17?
4.
17 to 21?
4.
So our difference is positive 4. Okay. Now, we're going to write the recursive definition first. So I'm going to write this definition using what we just got.
Which definition?
The recursive definition. So the recursive definition it's going to be, remember, all we're doing is we're plugging in A1 and D. So it's going to be AN equals my sequence, and my A1 is 5 when n equals 1. And the bottom part is a to the n minus 1 plus 4, where n is greater than 1. All we did was we rewrote the equation using what we just found from the sequence. Okay? And then our explicit definition is the same way, it's just written a little differently. We're going to plug in the two things that we know. So it's going to be AN equals A1 is 5 plus 4 times n minus 1. All I did again was I plugged in the values to the equation from up above. So now I'm going to backtrack. What is the 100th term? Okay, yep, we're going to look for A100, good. Okay, again, we're going to use the explicit definition to help us figure that out. Well, if A is 100, what am I plugging in? Remember, usually this stands for AN. So what am I? I'm going to plug in 100 for n, right? Because remember, n and 100 or n and this number right here should always match. So then I have 5 plus 4 times 100 minus 1. So I'm using this equation right here and plugging in 100 because that's the term I'm looking for. So now I solve what's first.
Parentheses.
Yep, so I have 4 times 99. 4 times 99 is 396. And then we add 396 plus 5 is 401. Okay. So we use the explicit definition to help us figure out what a certain number of term would be. If I was looking for, let's say, the 50th term, how would I find it?
Plug 50 in for n.
Plug 50 in for n to the same equation. Yep. Good. Another example we're going to look at is your example 26, number 26 in your book. Okay, this tells us 8 terms. Sorry, don't write that down yet. We need to talk about something first. Now we're talking about finding the sum. Now remember the sum definition. That is our S equals n times A1 plus AN divided by 2. That's our sum equation. Now we're going to jump to number 26. So number 26, it tells us we have 8 terms. Our A1 is 2, and our A8 is 74. In order to use this equation, we have to know what n is, we have to know what A1 is, and we have to know what AN is. Okay, so let's find those. What is our n? What does n stand for? What did we say n stood for? N stands for number of terms. How many terms are there?
2. 8.
There's 8 terms.
Oh, 8.
And then we want to know what A1 is. What's A1?
2.
A1 is 2. What is AN? What does AN stand for?
The last term.
The last term. What's the last term?
74.
It is 74. So we have 8 terms. So remember A8, that's our last term if we have 8 terms.
8's our last term.
Yep, because there's 8 terms. So our last term is 74. Okay, our 8th term in the sequence, which is the last one, is 74. Okay, now we have everything we need in order to use the equation up above. Okay, so we have S equals 8 times 2 plus 74 divided by 2. What needs to happen first?
Parentheses.
Yep, so we get 76. Next we,
Multiply by 8.
yep, so we have 608 divided by 2, and then we divide by 2 to get 304. So that is our sum of that particular sequence they were talking about. Do we remember what the Greek term is for sum? So this is just a random example I'm throwing at you. So it's that sigma n equals 1, and then our equation is 2n plus 1. So we still want to find the sum. We still want to use this equation here. Okay, so we need to find n, a1, and an. How many terms are in this sequence? Where do I get the number of terms from? I pull it from somewhere. I get it from the top. Yep, whatever number is sitting on the top of sigma, that is the number of terms that I have. Okay. A1, what does A1 stand for?
The first term.
First term. Do I know what that is just by looking at it? No, I have to find it. Okay. My first term is when n equals 1, so I need to plug 1 into n there. So I have 2 times 1 plus 1. What's 2 times 1?
1.
2 plus 1 is 3. So my A1 is 3. Okay, now AN, what does AN stand for? Last term. What am I plugging in for n this time? 4. Yep, so we're looking for A4. So I have 2 times 4 plus 1. What's 2 times 4? 8 plus 1? 9. So now I have all three things in order to use the equation from up above. Okay, so my sum equals 4 times 3 plus 9 divided by 2. What do I do first? 3 plus 9 is 12. 4 times 12 is 48. Divided by 2 is 24. 5. We have 2 more lessons. So we're on lesson 1.5. Okay. Lesson 1.5, that was the lesson that was all about graphing. Okay. How many different graphs were we looking at? How many different types of graphs we were dealing with? 3. What was one of them? Well, it's one that we're always used to. Linear, right? So let's focus on linear real quick. What form is linear in? What's the equation? Y equals mx plus b. What does that m stand for? Slope. What does the b stand for?
Base.
Nope. Where's our starting point at for all these? Y-intercept. Yep. Let's talk about what these pictures look like quick. If I have a slope that goes up like this, is that positive or negative? It's positive. If I have a slope that's negative, that's going down. Okay, let's talk about how we graph these. Where's my starting point for these? Where do I start graphing these? So you would think 0, 0, but where do I get my starting point at? Starting point is from our y-intercept here. So the b, which tells you the y-intercept. Where's the y-intercept going to be at? On the y-axis or the x-axis? Y-axis. Okay. And then how do we get all of the other points? What do we use to get all of our other points? Yep. Use the slope to find all other points. Remember, how do we read slope? Rise over run. Good. Okay, so you start with your y-intercept on the y-axis, whatever that b is telling you, And then you use your slope, rise over run, to get the rest of your points. Okay? And then your answer, what's my answer? What's my answer for these graphing ones? Where they
cross.
Yep, where the lines intersect. And then last thing, how do I write my answers? Coordinates. That was one of them, linear. There were two other ones. What are the two other graphs?
Wasn't there
What do they look like?
a U?
A U. That's our quadratic. I'm going to start with absolute value first. Okay, our V's. We're going to do absolute value first. What does absolute value look like?
V-shaped.
A V shape. So up is positive, negative is down. What does it look like in an equation? What do you see in the equation to give away that it's absolute value?
Lines.
The bars, right? Yep. This is what you see. Okay. So let's talk about how we graph this. I'm going to throw a specific example in here so we can keep referring back to it. 5y equals absolute value of x minus 6 plus 2. Okay, I'm going to refer to this example while we explain this. Okay. So to graph this, where do I get my starting point from? And there's one more. Yep, this is our transformations that we talked about in lesson 2. Okay, the numbers in the equation tell us where we get our starting point. Okay, now is the x with, is the 6 with the x or without? It's with, so do we think opposite or think normal? Opposite. What is minus 6 telling me? You go right 6. And then that plus 2, is that the y or the x? It's the y. So is that telling me up or down 2?
Up to.
Up 2. So the starting point that just gave me is 6, 2. On the graph, I go right 6, up 2. That's my starting point. Okay? Where do we get all of our other points from for absolute value?
So
Up 1 over 1, right? Because it's a v. All other points up 1 over 1 in both directions. And again, how do you check if you graphed it correctly? What should it look like?
V.
Yep, looks like a V. And then last thing, where do we get our answer from? What's our answer after we graph? Where they
Cross.
intersect or cross. And then again, how do we write our answers? Coordinates. Good. The last one we said earlier was the U's, which is our quadratic. Yep. Quadratic. What is the dead giveaway in an equation for a quadratic?
There's a second.
If there's a second or a squared. Yep. So remember, if it's positive, it's upright. If it's negative, it's upside down. Okay. There's two different versions of the quadratic equations. Okay. One of them is exactly like how we do absolute value. Okay, so if I write this example, I have x minus 6 squared plus 2. Okay, that example, we would get the same starting point as the absolute value. So our starting point is the same as absolute value. Okay, but to get our other points, are we just going up 1 over 1? how do we get all of our other points?
Up 1 over 1.
It's our step pattern, right? So all other points is our step pattern, which is what? 1, 3, 5, and 7. Okay, so for an example, that's telling me over 1 up 1, over 1 up 3, and so on. What would my next one be if I kept going? Over 1 up,
7.
look up here.
5.
Over 1 up 5. Yep.
Oh.
Okay. Now put a little break in your page, okay, because we got to talk about the other option of graphing quadratic equations. Okay, because if we had y equals, let's see, if we had y equals x squared plus 4x minus 2. How are those two equations different, these two?
There's an extra thing.
There's an extra x, right? This one we have to take a little differently. Okay, so to graph this one, how do we get our starting point? There's a specific equation we're going to use.
ABC.
Yep, we're going to do the ABC. It's our x equals negative b over 2a. Okay, so you use this method if it looks like that equation. What's my negative b?
-4.
Negative 4. Over 2, what's a?
X.
What's technically in front of the x? 1. Yep. So we have negative 4 over 2 times 1? 2. Negative 4 divided by 2? Negative 2. Okay. Is that my starting point?
No.
What do I need still?
We'll do the plug it back in. Plug it in
Yep.
for X.
I need the y value, right? So to find the y, I'm going to take this negative 2 that I found for x, and I'm going to plug it into both x's. Okay, so now my y is going to be negative 2 squared plus 4 times negative 2 minus 2. Highly recommend you write that out so we don't get lost. Okay, what's negative 2 squared?
-4.
4. 4 times negative 2? It's negative 8. And then I still have that minus 2. So if I did all of that 4 minus 8 minus 2, you get negative 6. Now do I have my starting point? Yes, because this is written as negative 2, negative 6. Okay, so a little bit longer of a process to get your starting point. Okay, but that is my starting point. Then, how do I get all of my other points? What do you mean by the same thing? Step pattern, yep. We're going to do 1, 3, 5, 7. So again, that's over 1, up 1, over 1, up 3, over 1, up 5, and then you kept going. Okay? And then lastly, where do you get your answer from?
Where they cross.
Where they intersect. And then, how do I write my answer? Coordinates. Good. Okay. The last lesson is lesson 6. And that was when we talked about linear systems and elimination. Okay. So let's look at number 35 in your book. We're just going to jump right into it. Let's look at steps first. What would step 1 be of elimination? Remember what step 1 is?
Find the opposite.
Step 1, look for opposites. Look for opposites, and you want them to be opposites and the same number. What's step 2? Let's say if you have opposites, what's the next step? Big addition. So if yes, big addition. If no, what do you do if you don't have opposites?
You're wrong.
Right, we have to change it, right? What do you have to do? Probably multiply? Yep, multiply to make opposites. And then you can do, once you have opposites, you can do big addition. Okay, and then 3 is you solve for the variable that is left. Solve for the variable. What do you do once you have that one variable? If you found one, how do you find the other? So say I found x, how do I find y?
Plug x in for x.
Yep, plug in value to other equation. Okay, specifically one you didn't touch. Okay, so following those 4 steps is what's going to help you. So let's look at an example. Okay. Not 35, I don't like that one. Let's look at example, I'm going to pull it from here. This one. If I have x plus y equals 9, and I have 2x minus y equals 6. Okay, so step 1 we said is what? Look for opposites, okay? Look at the x's. Are the x's opposites or do they match? Yes or no?
No.
No, what about the y's?
Yeah.
Yes, they're opposites because of positive and negative. Are they the same number?
No.
They're the same number, right? What's technically in front of the y?
1.
A 1, right? So they're the same and they're opposites. That's good, right? So since I have a yes, I can do big addition problem. What's 1x plus 2x? 3x. What happens to the y's? Cancel out. And then 9 plus 16?
9 plus 6.
Or sorry, 9 plus 6 is
15.
15. Yep. If we didn't get something to cancel out, can you move on?
No.
No, something always has to cancel out. Last step, divide by 3, x equals 5. Am I done?
No.
No. Underline that so you don't forget about it. We got to find y now. What do I do?
Plug 5 in for x.
Does it matter which equation? No, it,
Didn't change anything.
right, it always has to be one of the originals though, so I'm just going to pick that top one. I'm plugging in 5 for x. So I have 5 plus y equals 9. What's my one step to get y by itself?
Subtract 5.
Subtract 5. So I have y equals 4. Am I done? No. How do you write your answers?
As 5.
As coordinates. So you get 5, comma 4. Good. Remember, it always goes x and then y. Okay? Where it will look a little different. So if I give you another example here. If I have negative 4x plus 4y equals 16. And then I have negative x plus 2y equals 10. What's step 1? What do I want to look for first? Opposites. Are the x's opposites? Or the same number? No. What about the y's? No. So we don't have opposites. What do we have to look for now? We have to see what we can change. We want to turn one into the other. Can I turn negative 1 into negative 4? So what I'm saying right here in front of that x, that's technically a negative 1. Can I change a negative 1 to a negative 4?
Yeah.
How?
Multiply by negative 4.
Why do you say negative 4, not positive 4?
Because they have to be opposite.
Because we want them to be opposites, right? So we want to multiply this whole equation by negative 4. Could I have also changed the y's? I could have, okay, I just picked the x's. Okay, it doesn't matter which one you change as long as you get them to cancel out. Okay, so my new equation, make sure we're multiplying this number to all three. So I have 4x minus 8y equals negative 40. What do I do with that other equation? Rewrite it, yep. Negative 4x plus 4y equals 16. Check, do we have opposites? Yes, okay, that was the whole reason we did this. We now have opposites, so we can do
Big addition.
big addition problem. What happens to the x's?
Cancels.
They cancel, which is good. Negative 8y plus 4y.
Negative 4.
Negative 4y. Negative 40 plus 16. We get negative 24. Next step, divide by
Negative 4.
negative 4. So we have y equals 6. Positive 6, because we got negative divided by negative. Underline it, so you don't forget about it. What do I do with that?
Plug it into the one you didn't change.
Yep, I'm going to plug it into the one I didn't change to eliminate miscommunications. So I have negative 4x plus 4 times 6 equals 16. What do I do first?
4 times 6.
Yep. Negative 4x plus 24 equals 16. Next step,
Subtract 24.
subtract 24. So I have negative 4x equals negative 8. Last step,
Divide by negative 4.
yep, so I get x equals
Negative x equals 2.
x equals 2. Am I done?
No.
No. Last step is
Just make it as coordinates.
write it as a coordinate. So I have 2, 6. Okay.